In the previous lesson, we learned what a greatest common factor was and how to identify it in a pair of terms. And the reason we're learning about greatest common factor is because we want to be able to do the opposite of expanding through distribution. We want to actually do something called factoring, and that's just the opposite process. In other words, getting things back to a distributed type of form. So what we're doing in this lesson is we're going to look at three different ways we can do that. The first one is trying to find a monomial in a string of terms as the greatest common factor. So let's begin by remembering that a term has two parts, two key parts, the numerical coefficient and the literal coefficient, which can each be broken down into two more parts that make up four parts of every term. The numerical coefficient consists of a sign, positive or negative. If it's not present, we know it's positive. And a value that could be an integer, a decimal, a fraction, any value belonging to any number set. The literal coefficient consists of a letter with its respective exponent. If no exponent is present, we assume it's a 1. But the literal coefficient can also have multiple powers in it. We could have x cubed, y squared, z. And all of those pieces would be part of the literal coefficient. So this is a good review for us in looking at greatest common factor. So when I look at the terms 8x and positive 2, I notice right away that positive 2 does not have a literal coefficient. It's just a constant. So what I want to do is pull out the greatest common factor that is numerical to both of these terms. Or what's the biggest value that can divide into both 2 and 8? Well, 2 is a prime number, and 8 can be broken down into 2 times 2 times 2. So the greatest common factor between these two is simply the value 2. So I'm going to put the 2 out front here to identify it as the greatest common factor. And then I'm going to ask myself, what would I have to multiply 2 by in order to get 8x? Well, if I go back up to here and I modify this to be 8x, we know that that would mean 2 times 2 times 2 times 2 times x. So if I take out just this 2, I'm left with all of this. Multiplied out, this becomes 4x. And lo and behold, if I do distribute this 2 times 4x, I should get 8x. Now, what does this 2 have to be multiplied by in order to get this 2 up here? Well, we notice that there's nothing left over. That can be thought of as being multiplied by 1. So we can put a 1 here. So essentially what we're doing is we're going from the expanded answer back into what's called factored form, or the original question that you're used to seeing, where you would take a monomial in front and distribute it to both of the things inside. We're going from the answer back to the question instead of question to the answer. And we do that through identifying the greatest common factor. Let's look at the next example. We see that the two terms here are positive 10x squared and negative 7x to the first. So what is the GCF for both of these terms? They both have a numerical part, 10 and 7, and they both have a literal component here, x squared and x. Sorry, not 10 and 7, 10 and negative 7. So is there a number that divides into both 10 and 7? Well, the answer is no, because 7 is a prime factor, one that we looked at in a previous lesson. The only things that divide into 7 are 1 and itself. So numerically, the only value I can take out is a 1. So I'm going to show that. Okay. Now, when I look at the literal portion here, I have 10x squared that can be broken down into 2 times 5 times x, and I have negative 7x that can be broken down into negative 7 times x. So again, I'm reinforcing here, none of the numerical components are in common. That's why I've said, well, 1 is the only common factor numerically for these two terms. But let's look at the literal part. How many x's do they have in common? Now I'm going to replace these times signs with just a different notation for multiplication so we can see them more clearly. And you can see that they both have an x in common. So that is also part of the GCF. So I could choose to write it as 1x, or I could just write x all by itself if I wanted to. Then, what would I have to multiply this x by to get 10x squared? Well, look at all the things that are left over. There's a 10 and an x. Multiplied together, they give 10x. And sure enough, x times 10x would give me 10x squared. What would I have to multiply x by in order to get negative 7x? Well, the only thing that's left over here is negative 7, so I can put it in like this. And sure enough, if you distribute your answer, you should end up with the question. And you do in this case. Let's look at the next example. We have 30a cubed b. I'm going to write it here to break it down for you. And we have 20a squared b squared. And I said you will get to a point where you don't need to do this expansion to see what their GCF is, but for today's lesson I'll be explicit and show you where it comes from. So what can you break 30 down to in numerically? Well, half of it would leave me with 15. And 15 can also be broken down into the prime factors of 3 and 5. 20 has a prime factor of 2, which is great, and that leaves me with 10. 10 can be broken down into 2 times 5. So clearly, from a numerical GCF, I can see that they have a 5 and a 2 in common, or a greatest common factor of 10 if I'm only looking at the numerical part. So let's write that out in front here. The GCF between these two has a numerical piece that is a 10. Now, let's look at the literal piece. In the first one here, I have times A times A times A times B, and down here I have times A times A times B times B. Well, what do you see as the literal piece that they share in common, or their literal prime factors? Well, I see they both have two A's being multiplied by each other and a B. So together, that makes A squared B. Let's add that over here as the GCF. So this is the full GCF, or greatest common factor, for both of these terms, taking into account the literal portion of both of them, or sorry, the numerical portion and the literal portion. To finish factoring this, I need to take that GCF and multiply it by the remainders in order to be able to get back to 30a cubed b. Well, I know 10 times 3 would give me 30. There's the 3 over here that wasn't included in the GCF. And there's also an a left over. So a squared times a gives me a cubed, and b times 1 would give me b. Let's do the same thing here. I have numerically a 2 left over. That can be multiplied by 10 to get 20. And it looks like in the literal portion, I have a b left over as well. So again, do a quick check. If you multiply these two together, do you get 20a squared b squared? And the answer is yes, you do. Let's try one more. Let's look at these two and ask ourselves, can these be factored? Factored means, so far, in your understanding of factoring, is there a GCF in them? And if there is, pull it out and put it in front. So let's look at the numerical pieces. Is there a number that goes into both 3 and 8? Well, there's not, right? 8 is 2 times 2 times 2, and there's no factors of 2 and a 3. Do these two terms have any literal parts in common? Well, this has x times x. There's no x's here. This has y times y times y. There's no y's here. And in similar fashion, there's no w's in this one and no z's. So there is no GCF at all, and that is possible. And therefore, we would say this is not factorable up to this point in your factoring toolkit. We'll learn about some other factoring tools a little bit later. But right now, the GCF identification is your primary way of answering a question that says, factor this. Okay, let's see what happens if the GCF for some terms is not actually a monomial, but it is a binomial instead. going to put 2 examples up to start, and then I'll add the third one after we've completed these. So I have 2x times the quantity z plus 1, and I have 5y times the quantity z plus 1. So I notice that these are 2 different terms. They're separated by a sign, just like they were before, and these are all things that are being multiplied by each other. So when I look at the first one, 2x times z plus 1, it's exactly that. It's 2x times z plus 1. I'm going to keep the z plus 1 together in brackets. And if I break this one apart into its prime factors, I just have 5y all by itself, also times z plus 1. So what I notice this time is that the GCF for these two is right here. It's actually z plus 1. It's a binomial that they share in common. So let's put that binomial out in front. Now, what do I have to multiply z plus 1 by in order to get this portion? Well, look at what's left over, a 2x. And what do I have to multiply z plus 1 by in order to get this? Well, look at what's left over, a 5y. And that's it. That's how you would factor when the GCF is a binomial that happens in common. And you can check, if I do z plus 1 times 2x, I will get this portion of the question. And if I do z plus 1 times 5y, I will get this portion of the question. So again, you can check your answer simply by distributing to see if you get the original question. Let's try another example. 6 times x plus 3 minus 5y times 3 plus x. So again, when I look at these two things, these are two examples of things being multiplied together, okay, 2 little bundles. You'll notice that this is a 6 times an x plus 3 and a negative 5y times a 3 plus x. So is there a GCF? Well, the tricky one with this is that you might say no, because this x plus 3 and this 3 plus x are not identical. But are they? If I have x plus 3, is that the same thing as 3 plus x? Yes, it is. So what I could do to make this a little clearer is I could just rewrite this to show that the greatest common factor is in fact identical. So I'm going to write this as x plus 3 and minus 5y times, again, I'm just going to write this as x plus 3. And then I can see that, again, these two pieces have a greatest common factor of x plus 3. So if I remove it from each of them, what do I have to multiply by in order to get the question back? Well, I have to multiply x plus 3 times 6 in order to get this piece. I also have to multiply x plus 3 times negative 5y in order to get this piece. And this is called factored form, as is this one. Let's try one more example. This is 3x times y minus 1 plus 1 minus y. So, is there a binomial that is a greatest common factor here? Well, initially we might say yes. We might say these two maybe are just written backwards like the last example was. Before I go any further, though, I want to notice that there's no number in here, so let's assume it to be a 1 going forward. So let me ask you this. Is y minus 1 the same thing as 1 minus y? Well, if we were to pick any value for y, let's say y equals 3, and sub it in, do we get the same answer on both sides? And the answer is no. So these two things are not the same, but they're awfully, awfully close. Their only differences are that in this side, the y is positive, and on this side, the y is negative. In similar fashion, the 1 here is negative, and here the 1 is positive. So they just have opposite signs. So here's a really cool little thing that we could do so that the two things in pink circles could be the same. What if we multiplied this something by -1 in order to make them switch? Well, if I were to multiply the opposites of these, watch this. If I were to do -1 times this and -1 times this, I would end up what's up here. Now this is perfectly legitimate because these two pieces are in fact mathematically identical to one another. They're just expressed in different ways. So in my next line, how about we simplify this a little bit, and let's notice that +1 times -1, because these are all being multiplied by each other, could be simplified to read -1. And let's also recognize that if I were to change the order of these two around so that the y is first, it's going to read y minus 1. Take a look now at our common binomial. That's a GCF in both situations. Let's take it out. There it is. In order to get this piece up above, I would have to multiply y minus 1 by 3x in order to get it. Whoops. And to get this piece over here, I have to multiply y minus 1 times -1. And then this is in fact factorable. So this is a funky little trick. It might take you a few moments or watching it a couple times to see what happens, but it's easily identifiable when you look at the question and you see inside these pink circles that these are identical except for both terms have opposite signs. That's a little clue that you can do this trick to make the question factorable. All right, in the next video I'll finish up your notes for lesson 5.3.